Deep learning has revolutionized the way we process data. The vast repertoire of transfer learning models available allows everyone, from artists to researchers, to obtain deep learning models ready to be used for their specific applications. In particular, in the biomedical research field, the present standard is to take an existing architecture designed for natural image datasets and then fine-tune the model on the medical imaging data. However, recent works suggest that this does not necessarily result in performance improvements, and that the design of these models is likely to be suboptimal for the medical setting, which has led to the increasing popularity of neural architecture search to generate suitable architectures. However, automatic hyperparameter optimization presents a major flaw in these use cases. Unlike in natural image scenarios, it is oftentimes unfeasible to obtain large, representative medical image datasets, and the models generated via neural architecture search tend to overfit on their validation partitions. In order to palliate this effect, researchers oftentimes combine the populations of models generated into deep ensembles, which has been shown to increase the performance of the models in large, well-studied datasets such as CIFAR10, NIST, ImageNet, or COCO. However, the interaction of neural architecture search and deep ensemble learning has yet to be characterized in complex scenarios where the models present a high tendency to overfit on the validation partition of the datasets. Hi, my name is Adri Gómez and I am a PhD student from the University Carlos III de Madrid. I will present to you the main findings of our paper, Improving Transfer Learning by Means of Ensemble Learning and Swarm Intelligence-Based Neuroevolution. In this work, we wanted to show that combining the models resulting from a neural architecture search does not necessarily entail better generalization than that of the standalone models. To begin with, we used the CIFAR10 dataset to test the performance of transfer learning, deep ensemble learning, neural architecture search, and the combination, and compare our results with the literature. We compared the influence of architecture complexity and weight pre-training in transfer learning, different data and model weighting strategies for deep ensemble learning, and search length and population size for the neural architecture search and combined approaches. For the last two settings, we developed a new optimizer based on the artificial B-colony algorithm, specifically oriented to start the search from transfer learning models. As expected, we did not find any signs of overfitting, with all methods behaving the same in the validation and test partitions. The combination of deep ensemble learning and neural architecture search outperformed either technique on their own. Moreover, the combination of small models into ensembles outperformed bigger standalone models. This is relevant because it implies that the architecture searches could be limited to shallower models, reducing the time and resources required to obtain them while attaining the same or even better accuracies. Once we finished assessing the influence of all these parameters, we moved on to a problem of biomedical interest, the prediction of the misalignment of the detector in a computed tomography device. If the center of the detector is shifted with respect to the center of rotation of the device, we obtain artifacts in the reconstructed volumes. Deep learning models can be used to infer the misalignment out of these images, which can then be properly reconstructed by simulating the opposing shift in the projections via software. To train the aforementioned models, we generated a dataset using only 6 rodent studies, to each of which we simulated 25 misalignments during acquisition. In this scenario, we first went for a standard transfer learning pipeline and fine-tuned the pre-trained BGG11 and BGG19 models. Then, we employed neural architecture search to generate populations of models, both from scratch and by optimizing the two transfer learning architectures. Lastly, we combined each population into ensembles, pruning them based on the learner's validation accuracy. We also checked the test accuracy of every possible learner combination, to obtain the theoretically best proven ensembles and prove that no matter how you try to combine the models, sometimes it was better to simply employ the best one on its own. With just 6 original volumes, we expected a high degree of overfitting, which is exactly what we found. Most models generated via neural architecture search presented differences of an order of magnitude in their validation and test performances. The models that overfit the most were given more weight when combined into an ensemble due to their higher validation accuracy, which led to the ensembles generalizing worse than the best standalone learners, even when they outperformed in the validation partition. Moreover, the models generated from scratch presented higher overfitting, likely due to their longer search length and lack of a priori information, leading to architectures that evolved too tightly around the validation data. The lack of robustness of this method is further proven by the differences in performance on distinct validation partitions. From all this, we conclude that the combination of deep ensemble learning and neural architecture search outperforms the standalone models generated only provided that they present a similar, and ideally low, degree of overfitting. Combining the populations generated takes up negligible extra computational costs, and can even allow researchers to limit the search to shallower architectures, reducing the compute times required. However, the varying overfitting resulting from training on small and complex datasets hinders considerably the generalization capabilities of the ensembles. An astute model selection criterion might prove itself way more useful than any combination of the population. Reducing the variance of the generated models via deep ensemble learning might still prove itself useful for small dataset scenarios though, considering that the test partition can be as biased as the validation one. However, selecting which models to combine can pose a significant challenge, considering that deep ensemble learning hinders the interpretability of the individual learners, which is already significantly low when these have been generated through neural architecture search. Thus, we call for further research on how to create, validate, and prune these ensembles to really grasp when and how to apply these powerful methods to biomedical scenarios. We would love to invite you to read our contribution and check out the project's GitHub repository, and we are eager to discuss these topics with you at a conference. See you there!